All right, so the next thing we should talk about when it comes to math in VEX or programming in general, which is very important, is the cross product. And we actually talked about this in the bunting example. And basically what it means is when you have any kind of two vectors, and what's important here, they don't have to be 90 degrees to each other. They can be in any shape or form relative to each other. They basically build some kind of flat area, if you think about it. And the cross product is then a third vector that is calculated from that, and so to say 90 degrees from this flat area that the first two build. Now the green one is the cross product, and I can change the two lines any way I want, and you can see it still gets the same cross product, so it's not about how they are next to each other. That said, if the angle goes over a certain number, then the direction switches. In the end, it doesn't really matter, but I'm saying that because there is actually a rule behind that. And this is, if you try to recreate this with your finger, you can see in which direction the cross product will be going. This is my right hand, and this is why this is called the right hand rule. I'm saying this because actually there are different techniques how to calculate this. It could also be left-handed. This is right-handed. And in this case, it's to the back. Now just keep that in mind, the cross product has a certain direction based on those two vectors. But as a general rule, it goes away 90 degrees, either in the front or the back. And in this case, the rule that is used is the right-hand rule. So what do we use this for? Basically, as we've seen in the bunting example, to calculate the direction that we don't have. That's all I can say about that. And what this means depends on the case. What I'm usually using this most often is the following. If I have this sphere here, and let's say I want to calculate what the direction around this object is, then I could take a control object to have just something that I want to check it with. And the cool thing about the control object is that it's made of just one point. You could also use a sphere that is set to primitive. Then you also have just one, primitive, there it is, also just one point. I find the control a bit easier here in this case to understand, but it doesn't really matter. And now we use VEX to actually calculate the around vector of the sphere using the cross product. So the cross product in general, and this is again something I reminded myself with this big button, always use normalized vectors. And in this simple example, the question could be, okay, what vectors do I have that I can work with? So the whole command is called cross, and when you write this, you can see that it only just takes two vectors. That's all there is. So let's do this in a second, but first we need two vectors. Now the two vectors I would use here are one, the direction towards the sphere, and then a second arbitrary vector, which I would just set as an up vector upwards. And if you imagine a line between the surface of the sphere and my point here, and a vector that goes upwards, then the resulting cross product or perpendicular vector would be in this direction. And you will see in a second, this results in a vector that will always go around the sphere. Let's do this. So first of all, we need to calculate the direction towards the sphere. To do this, first we need to know where the sphere is, so to say. So what we do is we calculate P2, which we did a couple of times before, by using a min-pos of the second input where my sphere is in, relative to my current position on the point of my control node here. And then I will calculate the vector, I call it dir, maybe dir to sphere, so that it's clear, which is just a vector that we talked about before. It's just P minus P2, if I'm not completely wrong again, that should define the vector towards the sphere. Let's quickly check this by putting this onto an attribute, because now we can use this attribute to check our theory. And when I click on it, I should get a visualizer. Now it doesn't seem to do anything, and that is expected because usually whenever I create a vector for visualization, for some reason Houdini thinks it should be a color visualization. So let's change this to marker and then vector, and there it is. Now we have it. And let's turn this blue for now. And as you can see, as usual, I'm wrong with the direction. I don't know why I fail doing this every single time. And so it's the other way around. And now we can see this is now the vector from this point to the surface of the sphere. Let's quickly double check this. Yep, that seems to work no matter where my control node is. And now, of course, as I just said, let's make sure we normalize that, because we don't want this to be the exact same length as the distance. We want this to have a length of 1. So now the length, no matter where I am, shouldn't change. Yep, that looks good. And now the second vector I want to create is an up vector that are simply set to 0, 1, 0. And this is something to remember. It doesn't have to always be a vector that kind of comes out of the relationship of your geometries. It can also be an arbitrary vector that you define yourself. As we did before, the up vector is a very common thing. So now we should have a second vector called up. Let's visualize this as well. In this case, we were lucky that it understood at least that. Let's turn this green maybe. Let's normalize this one as well, even though it is already a length of 1, but just to make it a habit. There you go. And now we want to calculate the resulting vector that is the cross product of the two. And this is easy. We call this cross. And it's just those two vectors that we have normalized go into the cross. If you want to, be completely safe, you could make it a habit to do this. You always write them in with a normalize in front. Now I'm of course doing complete overkill. I'm normalizing it multiple times, which of course is nothing wrong. It's just unnecessary. But remembering it this way is probably the safest bet. And now what you get is a third vector called cross, which we haven't turned into an attribute yet. So let's do that. And now we should be able to visualize this. Of course, it doesn't work again because it thinks it's a color for some reason. So let's turn this into a vector. And there it is. There is our yellow. Yeah, let's leave it at yellow, why not? Our yellow cross product. Now, why is this interesting? Because if you look at it, when moving around the control, and I hope we can see that, it always points basically towards the tangent or around, so to say, the sphere. And this is why it's cool. It's now a vector that we couldn't find otherwise than with the cross product. Now, this is especially cool when we don't just do it with one point, but here it's the easiest to understand. This is why I started with that. If we just copy this code, we can also do the same thing with multiple points. So for example, we take our sphere and create a grid, let's say, around this sphere. And then we scatter all kinds of points on that. And then we can just copy this code because this will work with every point we give it, not just the first one. And now you can see all our visualizations are visible for each point. What we can quickly do is make them a bit shorter, at least the vectors, and maybe some of them we also don't need. So we don't need the up or the dir, and the cross product I just shortened to 0.2. And here you can see what the main use case for a cross product is. We can now calculate a direction around our sphere. And of course, this also works with other geometry that is more complex. There you go. And this is really the cool thing. As you can see now, this around logic also works with more complex shapes. And this is why it's so cool and so useful. You can actually flow around an object no matter how complex it is. Let me increase the point count, and here you can see it. And this, of course, you can imagine is super helpful and useful for all kinds of stuff. For example, we could use this to simulate some kind of planet or something. So what I have here is a sphere, not a toy, just a sphere, and an area with points, scattered points, and then the basically exact same code we just wrote, just a bit more directly by skipping the internal variables and directly go into the attributes, but it's the same logic. And what I did is I just copied that code and put it into a popnet. And the cool thing is, without anything else in this popnet, I just dropped a pop wrangle, did the same thing. The only difference here is that I used the direction as a velocity. And you can imagine what this will do. It will move the points around my planet. One thing to keep in mind, whenever you drop a pop wrangle though, of course I want to have access to the sphere somehow, and the sphere here is connected to the second input of my PopNet, make sure that you remember that you have to change the inputs, because by default a pop wrangle has no input set. So what you should do is the second input of your PopNet you should also put as a second input of your pop wrangle, so that it can actually access it. This is something you can stumble over if you're not aware of this, and this is what I did here. So the second input is also the second context geometry, otherwise it can't find this min-pos here of the first line. So once this is set up, you can actually see that this can also be a cool thing of running your simulations, because now every point that is, by the way, constantly emitted on top is rotating around my sphere here. And of course, what is interesting, because, you know, again, the right hand rule, it depends basically from which side you look at the vectors. The points inside of our sphere are actually moving in the opposite direction. Of course, if you want to change the direction, by the way, I think it's obvious what to do. You just add a minus in front of this, and now boom, the direction, if I rewind, will be the opposite direction. And of course, if you wanted to simulate some kind of, I don't know, meteor ring or whatever, or however those are called, instead of using a grid, of course, you could use something like maybe a circle, and then maybe you turn it into a curve, give it a bit of subdivisions, and then with a poly extrude you can extrude it outwards. That could be a good solution to have, you know, a certain area of points that you want to scatter from, because this will now be where the points are scattered. And of course you would probably not constantly scatter them, but would already have a start amount. You know, that's a different topic, but you can see here this is a relatively easy way of doing this relative to the sphere. And sure, you can do this with a pop axis force or something, but the neat thing here is that this will, you know, apply to whatever object you give it. So if we have, you know, our toy as a planet again, for example, then you will see that the points will move differently around it. And this, of course, is something you can't do with a pop axis force anymore. So a pretty neat technique to create, you know, around vectors, the cross product. And last but not least, keep in mind you cannot just set the velocities directly in a pop simulation, but you can also use a pop advect by volumes and use a velocity field. And this velocity field can then be filled with a volume wrangle, also with a cross product. And I'm adding the direction, as you can see here, with an attract parameter. And then it looks like this. I create a velocity field in a volume that creates this kind of direction. And on top, I can add all kinds of other directions. For example, a direction towards the object, and also add a curl noise to it. So you can also use those techniques to fill a velocity field and then use a pop attract instead. And then it could look like this, that you have a force that is, you know, moving the points around a sphere. But since we added some kind of curl noise and also some attraction direction to the final velocity, you can make this a bit more interesting. And basically what this is then is a pop axis force that you build yourself. So maybe this could be a nice little homework for you to try to figure out how to build this with a velocity field. And here quickly is the code for this that I used. And when you look at the setup, you should be able to figure this out yourself. So yeah, let's finish here. I hope this is helpful. There's much more to say about this. I added a couple of interesting links on the right, but this is how the cross product works in its essence. And I hope this is helpful. Thanks very much and see you later. Cheers.